Transient on transmission line. In a computer network, pulse signals may be sent through the line. From Fourier analysis, a pulse can be regarded as a superposition of waves of many frequencies, that is, the harmonics as we usually call it. Sending a pulse signal on the line may be regarded as the same as simultaneously sending waves of different frequencies. The transitional period for the current and voltage on the line to reach steady values when a pulse is applied to a transmission line is called transient. Consider a voltage source connected to a transmission line through a switch. At the end of the transmission line, we have a termination impedance ZL. At time t equals to 0, the impedance at the source end is only the characteristic impedance of the transmission line, or Z0. Because at time t equals 0, the effect of the load impedance ZL is not felt yet. So in this condition, we can calculate what is the voltage at time t equals 0, or V0, and also the current I0 at time t equals 0 by using circuit theory. We can find the voltage V0 using voltage divider rules, and as for the current I0, it is simply the voltage divided by the total impedance of Zg plus Z0. This is the solution for current I0. It is equal to the source voltage Vg divided by the total impedance Zg plus Z0. Remember, this is the at time t equals to 0, therefore the impedance is Z0 instead of the input impedance of the transmission line. The initial voltage at time t equals 0, V0, is equal to I0 times Z0, which is equal to Z0 times Vg divided by Zg plus Z0. After the switch is closed, wave I plus is equal to I0. That is the incident current. And V plus is the incident voltage, is equal to V0. This wave propagates towards the load at the speed given by U equals to 1 over square root of LC, where L is the inductance per unit length and C is the capacitance per unit length of the transmission line. Since the speed is finite, it takes some time for the positively traveling wave to reach the load and interact with it. The presence of the load has no effect on the wave before the transit time given by T1 equals to L over U, where L is the length of the transmission line and U is the propagation velocity of the wave. At time t1 seconds, the wave reached the load. The voltage at the load is the sum of the incident and reflected voltages. voltage at the distance z equals to L at time t1 is given by V plus V minus, where V minus is the reflected voltage given by rho L times V naught, where rho L is the reflection coefficient at the load. That gives us 1 plus rho L times V naught. See, we can do the same for the current, except that in the case of current, the reflection coefficient is negative. So we have I naught minus rho L times I naught. That gives us 1 plus rho L times I naught, where rho L is the reflection coefficient at the load given by ZL minus Z naught divided by ZL plus Z naught. The reflected wave at the load will then travel back to the generator, and it will reach the generator at time t equals to 2t1. So at time t equals to 2t1 at z equals to 0, that is the location of the generator. Again, we have two voltages. One is the positive going wave and another one is the negative going wave. Earlier, we have a wave reflected at the load. That wave has a voltage given by rho L times V naught, reflection coefficient times the original incident wave. But when this wave reaches the generator, some wave will be reflected, and that reflected wave will be positive going, or going in the positive direction, and the voltage level is given by rho L times V naught, that is coming from the earlier reflected wave, multiplied with the reflection coefficient at the generator, rho G, where rho G is given by ZG minus Z naught divided by ZG plus Z naught, where ZG is the impedance of the generator. The voltage going in the negative direction, that is the voltage that comes from the load or reflected from the load earlier. That voltage is 1 plus rho L times V naught that we get earlier. 1 plus rho L V naught is the voltage that is reflected back to the generator. We can do the same for the current, except that we just replace V with I and rho with negative rho. It is easier to keep track of the reflections using a bounce diagram or lattice diagram. This is how it looks like. Initially, when the switch is closed, using voltage divider rules, we get a voltage V naught at the input terminal of the transmission line. This voltage V naught is the positive going wave or incident wave, and this wave travels to the load, and at time t1, this wave is reflected. The reflected voltage is given by rho L times V naught. But at the load end, The total voltage is V0 plus rho L V0. That is the incident wave plus the reflected wave. The reflected wave rho L V0 then travel back to the generator and reach the source end at time 2t1. This wave is then reflected back. The magnitude or voltage of the reflected wave is given by rho L V0 multiplied with the reflection coefficient at the generator. Again, this wave will travel to the load and reach the termination at time 3t1. After that, a fraction of the wave is reflected again, given by rho G rho L V0 multiplied with rho L. That is the reflection coefficient of the load. And we can do the same at the generator at time 4t1. Wave is reflected, so we multiply this voltage with rho G and so on. We can do the same for the current. As I said earlier, we just replace V0 with I0 and rho L with negative rho L, rho G with negative rho G. Let's look at an example. For the transmission line shown, calculate and sketch the voltage at the load and generator ends for time t from 0 to 6 microseconds. And also for the current at the load and generator ends for time t from 0 to 6 microseconds. We have a transmission line with a characteristic impedance of 50 ohm. And the propagation velocity is 10 to the power 8 meter per second. The length of the transmission line is 100 meter. The transmission line is terminated by a load resistance of 200 ohm. At the source end, we have a voltage of 12 volts with a generator resistance ZG of 100 ohm. The switch is closed at time t equals to 0. Let us first calculate the reflection coefficient at the generator and also at the load. At the generator, the reflection coefficient is given by Zg minus Z0 over Zg plus Z0. That gives us 1 over 3. And at the load, the reflection coefficient is given by ZL minus Z0 over ZL plus Z0, and that gives us 3 over 5. The transit time, that is the time taken by the wave to travel from the source to the load. T1 is given by L over U, where L is 100 meter and U is 10 to the power 8 meter per second. So the transit time T1 is 1 microsecond. The initial voltage at the generator N is given by this formula, which is basically the voltage divider rules that we study in circuit theory, where the impedance connected to the source is Z0. because at time t equals to 0, the effect of the load is not felt yet. So we get V0 equals to 4 volts. Let's draw the voltage bounce diagram. So initially the voltage that is transmitted into the transmission line, V0, is 4 volt. This 4 volt transient voltage travels towards the load and reach the end at time t1. Due to impedance mismatch, we have a reflection coefficient of 3/5. So the reflected wave will be 3/5 multiplied with 4, that gives us 2.4 volt. But at the load end, the total voltage is V plus V minus. That means we get a voltage of 4 plus 2.4 or 6.4 volt at time t1. The reflected wave of 2.4 volt in the form of a transient is reflected back to the generator and reach the source end at time 2t1. And the reflection coefficient at the generator is 1/3. So the voltage that is reflected at the generator will be 1/3 times 2.4. That gives us 0.8 volt. But the voltage at time t equals to 2t1 at the generator will be given by this voltage 2.4 volt and also the reflected voltage 0.8 volt plus the initial voltage of 4 volt. So that gives us a voltage of 7.2 volt. This reflected voltage of 0.8 volt travel to the load at time t equals to 3t1. And because the reflection coefficient at the load is 3/5, the reflected voltage is 3/5 times 0.8 volt, which gives us 0.48 volt. But at time t equals to 3t1, the total voltage at the load end is the original voltage of 6.4 volt plus the positive going wave of 0.8 volt and the negative going wave of 0.48 volt. So that gives us a voltage of 7.68 volt. This reflected voltage of 0.48 volt will then travel back to the generator at time t equals to 4t1. Similarly, some wave is reflected. That reflected voltage is 0.48 volt multiplied with the reflection coefficient of 1/3. That gives us 0.16 volt. The total voltage at the source end will be given by the earlier voltage of 7.2 volt plus the voltage of the incoming wave, which is 0.48 volt, and the voltage that is reflected back towards load of 0.16 volt. That gives us a voltage of 7.84 volt. We can continue the process and we will find that at time t equals to 5t1, the voltage at the load N will be 7.936 volt, and then at time t equals to 6t1, the voltage at the generator will be 7.968 volt, and then at 71, the voltage at the load N will be 7.986 volt. As time goes, the voltage at the load N and also the voltage at the source N will become steady value, which doesn't change with time anymore. And we will find that the voltage at the source N is equal to the voltage at the load N if the voltage source is a DC voltage of 12 volt. We can do the same for the current, which we will do later. But first, let us plot the voltage at the generator N and the load N. Based on the voltage that we get here at time t to 0, we have 4 volt at the source N, and then at time 2t1 we have 7.2 volt. At time 4t1 we have 7.84 volt, and at time 6t1 we have 7.968 volt. If we plot out the voltage, we get 4 volt followed by 7.2 volt at time 2t1, which is 2 microseconds, and then at 4 microseconds we have 7.84 volt. At 6 microseconds we have 7.968 volt. It will be shown later that at time t equals to infinity, the voltage becomes stabilized at 8 volt. The reason why we have 7.2 volt at time t equals to 2 is because we have a reflected voltage of 2.4 volt coming back from the load. The 2.4 volt plus 4 volt plus the voltage that is reflected at time t equals to 2t1, which is 0.8 volt. So we have 0.8 plus 2.4 plus 4. That gives us 7.2 volt. And then at time t equals to 4t1 or 4 microseconds, we have a wave of 0.48 volt coming back from the load, and then we have a wave reflected towards the load with a voltage of 0.16 volt. So the voltage at the generator will be 0.4 volt plus 0.16 volt plus the earlier voltage of 7.2 volt. Alternatively, you can add up all these voltage, 0.16 plus 0.48 plus 0.8 plus 2.4 plus 4. Yeah, we will get the same answer of 7.84 volt and so on. As for the voltage at the load N, At time t equals 0, there is no voltage at the load end. The voltage is 0 because the voltage from the generator will only reach the load at time t1. Between 0 to t1, the voltage is 0. At time t1, we get a voltage of 6.4 volt, and then at 3t1 we get 7.68 volt. At 5t1 we get 7.936 volt, and at 7t1 we get 7.986 volt. So if we plot out the waveform at the load end, this is the voltage step that we get. From 0 to 1 microsecond, the voltage is 0, and then it go up to 6.4, and then at 3 microsecond it go up to 7.68, at 5 microsecond it go up to 7.936, and then at time t equals to infinity, that is at the steady state, the voltage will stabilize at 8 volt. Similarly, the reason why we have 7.68 volt is because we add 4 volt, we add 0.8 volt with 0.48 volt, and that is the reflected wave, and then we add it to the earlier voltage of 6.4 volt. Yeah, we can do the same for time t equals to 5t1 and time t equals to 7t1. So this is the voltage at the load end that we get. The reason why at time t equals to infinity, that is the steady state, the voltage will stabilize, because in this situation we have a DC problem. That is the effect of the transmission line is negligible. Yeah, we have a situation where the load ZL is now connected to the generator directly, because at time t equals to infinity, the voltage everywhere along the transmission line will be the same. So we can use circuit theory to find the voltage across the load ZL, and this voltage is also the same at the source end, because in this steady state condition, the voltage along the transmission line is the same everywhere. So the voltage at the load end is equal to the voltage at the source end. Using voltage divider rules, we get a voltage of 8 volt. This is the voltage at the steady state, or at time t close to infinity. We can now work on the current waveform at the source end and also the load end. As we said earlier, to find the current waveform, we can use the same formula except that we replace the reflection coefficient with negative value. So earlier we had the reflection coefficient at the generator was 1 over 3. We just replace that with negative 1 over 3. And the reflection coefficient at the load end, we just replace it with negative rho L, which is negative 3 over 5. The initial current at time t equals 0 is given by V0 over Z0, where Z0 is the characteristic impedance of the transmission line, because at time t equals to 0, we do not have any reflected wave. We only have V plus, no V minus. And V plus is given by V0 over Z0. That gives us 80 milliamp. Because at time t equals to infinity, that is the steady state, we have a situation where it does not matter where the load impedance is connected along the transmission line, because the voltage everywhere along the transmission line will be the same at time t equals to infinity. So we have current given by the voltage divided by the total impedance of Zg plus Zl. That gives us a current of 40 milliamp. This is the bounce diagram. So instead of the voltage V0, we use the current I0 of 80 milliamp. And for the reflected current, it is given by the reflection coefficient multiplied with the incident current of 80 milliamp. Of course, we need to add a negative. Alright, so the procedure is the same as the case for voltages at time t1, 2t1, 3t1, 4t1, and so on. So that gives us a current at the source end initially was 80 milliamp, and at time 2t1, because of the reflected current and current that is re-refracted, which is 16 milliamp. So we have a total current of 80 plus negative 48 plus 16. That gives us 48 milliamp. And then at time 3t1, this 16 milliamp of positive going wave is reflected. The reflected current is negative 9.6 milliamp. So the total current at the load end is 16 plus negative 9.6 milliamp plus the current earlier, which is 32 milliamp. That gives us 38.4 milliamp, and so on. So based on this, all this current that we get at the source end, we can plot the waveform of the current. Initially at time t equals 0, we have 80 milliamp. At 2 microseconds, the current dropped to 48 milliamp, and then at 4 microseconds, the current dropped again to 41.6 milliamp, and so on. Finally, the steady state current stabilizes at 40 milliamp. We draw the current waveform as a negative transient when the current is negative 48. The same goes for the case when the current is negative 9.6 milliamp. We plot it as a negative waveform so that we can find the total current by adding this to this, right, and also to the original current of 80 milliamp. That gives us 48 milliamp and so on. The same goes for the current at the load end. Between time t equals 0 and 1 microsecond, because the incident wave has not reached the load, the current is 0. At time t1, when the wave arrives at the load, the current will rise to 32 milliamp. And then some wave is reflected back. The reflected current is minus 48 milliamp. And when this wave reach the generator, it is reflected again. The reflected current is 16 milliamp. Therefore, at time t equals to 3 microseconds, the total current will be given by 16 plus minus 48 plus the earlier current, of 32, so that gives us 38.4 milliamp as we get here. 32 plus 16 minus 9.6 gives us 38.4 milliamp at 3T1.